hot air ballooning, the warmth of a cozy fire, the eruption of a volcano, and life itself are all dependent upon heat. Flying high in a beautifully colored hot air balloon is possible because of heat. The gas flame is used to heat the air, which causes it to expand. It doesn't take long before the light material of the balloon can be lifted up by this expanded air. The hot air is not as dense or heavy as the cold air around it. The hot air is more active and requires more room than cold air, so much of the air is pushed out of the balloon. As a result, there is less air in the balloon than the air around it, and the balloon is buoyed upwards. A wood fire in a fireplace is an example of heat produced by burning. There are many other fuels that are used for burning, such as coal, oil, and gas. The energy is used in a variety of ways, from warming a house to generating electricity. This power plant uses the energy from a nuclear reaction to produce heat to boil water that turns to steam. The steam is then forced past the turbine blades of the generator. The blades spin and cause the generator to turn, producing electricity. Other power plants use other fuels, such as coal, to heat the water to make steam. So much of the electricity that we use on a daily basis is possible because of heat. Hot lava erupts and pours across the land as a result of tremendous pressure in the interior of the planet. Temperatures are so great that rock melts and flows from the mouth of a volcano. However, the most important source of heat is the sun. In fact, all life on our planet is dependent on the heat from the sun. There would be no life on Earth without solar energy. The sun's heat keeps the temperature within a range that is suitable for life as we know it. The heat energy from the sun keeps the water cycle operating. The water cycle is nature's way of maintaining fresh water for the Earth. The heat from the sun heats the water of the Earth's oceans and lakes so that it evaporates. This means the liquid water molecules move faster and change from their liquid form to a gaseous form. As a gas, the water vapor rises into the air, leaving behind salt and other chemicals, so that the water vapor is clean and pure. As the water vapor rises and becomes cooled, it may begin to condense around dust particles and eventually return to the Earth's surface as a form of precipitation, rain, or snow. So in more than one way, the energy from the sun is crucial to life on Earth. The words temperature and heat are often used to mean the same thing. Actually, they are related, but they don't mean the same thing. Temperature is used to measure how hot or cold an object is. Objects with the same temperature can give off different amounts of heat. Think about this situation. Here are 3 beakers with different amounts of water in each. The temperature is exactly the same in each beaker. The question for you is, which beaker contains the greatest amount of heat energy? Well, the largest beaker contains the greatest amount of heat energy. Imagine if the temperature had been much higher, such as boiling. If the water were to spill on you, the large beaker would hurt the worst because it has a greater mass of water, and therefore, even though the temperature is the same in all 3 beakers, the larger one has more heat. Heat is determined by the temperature and the amount of the substance. Temperature is measured with a thermometer, which is usually a hollow tube with either mercury or colored alcohol in it. The fluid will move up or down the tube, depending upon the temperature of the substance being measured. It works like this. All matter is made up of atoms and molecules that are in constant motion. We can't see this motion because the atoms and molecules are so very small. A piece of paper is 1 million atoms thick. When matter is heated, the atoms or molecules move faster with greater strength. They bounce around more and are more active. When the thermometer touches the object, the motion of the object's molecules is transferred to the molecules of the thermometer fluid. The fluid then either expands, because the molecules are moving faster, or the fluid contracts, because the molecules are moving slower than before. When the fluid expands, it moves up the thermometer and registers a high temperature. The motion of atoms and molecules in matter is called kinetic energy. So temperature measures the average kinetic energy of a substance. The temperature scale used by scientists is called the Celsius scale. It is based on the freezing and boiling points of water. On this scale, the freezing point of water is 0 degrees, and the boiling point is 100 degrees. The scale is then divided into 100 equal degree markings. In America, the Fahrenheit scale is used in daily life. This scale uses 32 degrees as the freezing point of water, and 212 degrees as the boiling point of water. Americans are so used to the Fahrenheit scale that when we see temperatures given in Celsius, it seems confusing. However, most countries of the world use the Celsius scale. There is another scale called the Kelvin scale. This scale is based on absolute zero. Absolute zero would be the point at which all atomic and molecular activity would stop. There would be no kinetic energy. On the Celsius scale, absolute zero is minus 273 degrees. The units in the Kelvin scale are the same size as the units on the Celsius scale. So freezing water is 273 Kelvin, and boiling water is 373 Kelvin. There are no negative numbers on the Kelvin scale. Heat is not measured with a thermometer and in degrees. There are different units used to measure heat energy. One is called the calorie. The calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. Food energy is measured with this unit. The unit used to rate food is actually a kilocalorie, which is 1,000 calories. Notice that when you look up the calories on a package of an item of food, the word calories is shown with a capital C. This is to indicate that it is 1,000 calories. This can of vegetable soup indicates that it contains 90 calories of energy, which are released when the soup is eaten and digested. People get the energy their bodies require from the food they eat. A special instrument is used to measure calories. It is called a calorimeter. Basically, it is made of 2 chambers, one inside the other. The outer chamber holds water. The inner chamber is where the food sample is burned. The temperature of the water in the outer chamber is measured before and after the sample is burned. Then the difference in temperature is multiplied by the amount of water to determine the calories of heat given off. The standard unit used to measure energy is the joule. Energy is the ability to do work. Work is measured by multiplying force by the distance it is exerted. In the scientific community, this means newtons of force times the distance measured in meters. The basic unit for work is the joule, which is 1 newton of force exerted over 1 meter. 1 joule equals 1 newton meter. Since work and energy are closely related, the joule is used to measure energy as well. 1 calorie equals 4.18 joules. Another unit used to measure heat energy is the British thermal unit, or BTU for short. This unit is defined as the amount of heat energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. This unit is often used to measure the energy output of heating and cooling systems such as furnaces, ovens, refrigerators, and air conditioners. This furnace is rated at 124,000 BTU per hour. The BTU is primarily used in the United States, as the joule is used throughout the rest of the world. Both the joule and BTU can be used to compare the energy output of various fuels. For instance, a gallon of gasoline equals 124 BTUs. A gallon of diesel fuel equals 139 BTUs. 1 gallon of propane equals 91 BTUs. Prices can be determined for each of those fuels, and then the most efficient fuel can be determined. We already know that heating something causes the temperature to rise, but there are other changes that occur in the presence of heat. When most objects are heated, they expand or get bigger, and when they are cooled, they contract or get smaller. Here is a demonstration of that principle. The metal ball fits easily through the ring. Now the ball is heated for a few minutes. When we try to pull the ball through the ring after heating, it doesn't want to cooperate. If we cool the ball in this water, it contracts and is easily pulled through the ring. You may have noticed that on bridges there is a metal grid at different key points. These gaps are called expansion joints, and they allow for expansion and contraction of the bridge during the summer and winter. Maybe you have noticed that the wires between telephone poles are not pulled tight, but sag. Well, now you know why. The wires must be able to expand or contract depending on the weather. When architects plan and design buildings, they must take expansion and contraction of the materials into consideration. So joints are made to be flexible because buildings are expanding and contracting all the time as the seasons change. Another change that occurs when matter is heated is a change in phase or state. If we heat ice, it will melt and change to water. It has changed from a solid, as ice, to liquid, water. If we continue to add heat to the water, it will eventually boil and evaporate into a gas called water vapor. This is another change of phase from a liquid to a gas. A change of state from a liquid to a gas is called vaporization. There are two kinds of vaporization, boiling and evaporation. Boiling happens throughout a liquid. Different liquids will have different boiling points. Boiling and melting points are properties that can be used to help identify a specific substance. Evaporation occurs at the surface of a liquid and happens at a temperature below the boiling point. You may have noticed that the water level of an aquarium varies. If left alone after a few days, the level will go down because some of the water will have evaporated. After exercising, you perspire. This is the way your body cools down. The perspiration evaporates from your skin using energy from your body in the process. Heat energy is lost, and a cooling effect results. These changes of state all include adding heat to the substance, which is referred to as an endothermic change. An endothermic change of state requires the absorption of heat. If we take heat away from something by cooling it, we can also change the state of the substance. This is referred to as an exothermic change. If we cool steam by bringing it in contact with this glass of ice, the steam will condense on the outside of the container. The steam changes from a gas to a liquid as its temperature drops and it loses heat energy. An exothermic change happens as a result of removing energy from a substance. Heat is a measure of the energy of a substance based on the temperature and the amount of the substance. So if heat is removed by cooling, energy is lost, and if the cooling continues, a change of state can occur. Maybe you have noticed that a nice cold glass of juice or soda leaves a ring on the table after sitting out for a while. The glass isn't leaking and you didn't spill. In fact, the ring isn't juice or soda. It's water. Water vapor in the air has condensed onto the outside of the glass because the temperature of the ice-cold drinking glass provides a cool surface. The water vapor as a gas has changed to liquid water. Condensation is an exothermic change because heat energy is removed. Some substances can change directly from a solid to a gas. This is called sublimation. Dry ice is an example of such a substance. Dry ice is carbon dioxide in a solid state. It is very cold and is often used to keep medicine, food, or ice cream cold without getting them wet. That's because it skips the liquid state and goes straight to a gas. No puddles. Sublimation requires adding heat, so it is an endothermic change. During changes of state, the temperature of a substance remains constant. For instance, when water is boiling, the temperature stays at 100 degrees until all the liquid water has boiled away or changed to water vapor. Heat travels from one place to another in one of three ways: conduction, convection, or radiation. In solids, heat can travel from one particle to another. This is called conduction because the heat is conducted from one particle to another. For instance, if we hold a nail in a flame, after a short period of time the nail will become too hot to hold. The flame has caused the particles at the end of the nail to vibrate vigorously. This vibrating passes from one particle to another until it has passed throughout the nail. Metals conduct heat very well. Some solids, such as wood, paper, cork, and styrofoam, are poor conductors of heat. They are called insulators. Wood is often used as the handles for frying pans because it is a poor conductor of heat energy and protects your hands from the heat of cooking when you handle the pan. Convection is the way heat is transferred with liquids and gases. When a liquid or gas is heated, the particles do more than just vibrate. They move around to new locations. In the case of water heating on a stove, the bottom of the pot is heated, heating the water at the bottom, which begins to vibrate and move around. It becomes less dense and rises to the top of the pot. Cold water moves in to replace the heated water. This continues until all the water is heated and circulating. For either conduction or convection to work, particles of matter must be present to vibrate and move around. However, heat can also travel without matter present. Heat from the sun travels through the emptiness of space. There are no particles of matter in space, but heat can still travel as waves of radiant energy. This kind of heat transfer is called radiation. Heat moves from warm areas to cold areas. We use insulation in our homes to keep the heat in, not the cold out. The heat wants to move to the colder outside during winter, so we try to cut down on heat loss. Something that slows down the movement of heat is called an insulator. Certain materials, such as wool, plastic, and wood, are poor conductors of heat, so they make good insulators. Fiberglass is used in attics and walls of homes to slow down the movement of heat from the warm interior to the cold outside. Snow is a good insulator. That's why the Inuits build their winter igloos out of snow. A thermos bottle is a perfect example of a device that is designed to slow down all three forms of heat transfer. conduction, convection, and radiation. The thermos bottle is made of 2 layers of glass that are separated by a vacuum, which is the absence of air or other gases. Glass is a poor conductor of heat. We can demonstrate that glass is a poor conductor with this experiment. We will boil water in this test tube while holding the other end of the test tube. The vacuum is a wonderful insulator because there are no particles for the heat to vibrate. The glass is silvered so that it reflects radiated heat back to the inner container. When something hot is poured into the thermos, it will stay hot for hours. Cryogenics is the study of the behavior of matter at extremely low temperatures. Matter can be affected by low temperatures, as demonstrated with liquid nitrogen or dry ice. Nitrogen, which is normally in a gaseous state, can be liquefied at a temperature of 77 Kelvin. When objects are brought into contact with liquid nitrogen, the extreme cold changes the structure of the object. For instance, a flower may become so stiff and brittle that it smashes to pieces when dropped. Liquid nitrogen is dangerous, so people must be very cautious when working with it. If liquid nitrogen isn't available, you can create similar effects using dry ice and acetone. Dry ice is the solid form of carbon dioxide. It is at the temperature of minus 72 degrees Celsius. These extreme temperatures can cause severe burns, so be sure to wear gloves and do not touch the dry ice. You may have seen dry ice used as part of Halloween decorations. It creates a very impressive mad scientist lab effect. Put some grapes in and let them sit for a few minutes. Use forceps to carefully remove a grape and drop it on the floor. It bounces around like a marble. Put a banana skin in the fluid. Again, use the forceps to remove it, and then smash it on a table. Objects submerged into these cold temperatures will become very brittle as the water inside the object freezes. A balloon is submerged and it becomes deflated. Can you explain why? As the air inside the balloon loses heat, its atoms and molecules slow down. The air doesn't require as much space, so the balloon deflates. When the balloon is brought out of the dry ice, it will gradually reinflate. Today, we have looked at heat and touched upon some of the important ways it affects our lives. Heat is an energy form that all living things depend on. The food we eat is turned into heat and energy for our bodies to function. The food comes to us because of the sun's warmth and light. Now it is time for the program quiz. Try to determine if the examples given are examples of heat transfer by conduction, convection, or radiation. Example 1. The spoon is too hot to touch after sitting in the hot soup. Is this an example of conduction, convection, or radiation? Example 2. The moon's surface becomes hot. Is this an example of conduction, convection, or radiation? Example 3. Your feet hurt after walking barefoot across the beach. Is this an example of conduction, convection, or radiation? Example 4. Bacon cooks in the frying pan. Is this an example of conduction, convection, or radiation? Example 5. The room becomes warm when the furnace is turned on. Is this an example of conduction, convection, or radiation? The next 3 questions are short answer questions. Question 6. Sidewalks are built with spaces between each section. Why? Question 7. The cap on the jar is stuck, but if we run it under hot water, we can unscrew the metal cap. Why? Question 8. The level of the water in the aquarium goes down each day. Why?